This is the more comfortable section, but that doesn't mean that if you feel like you're not more comfortable, you won't learn things here. So let's get started. Do you have slides going right into things? Or am I about to just take it right now?
Yes.
Switching laptops.
You don't want to introduce yourself, Rob?
Oh, I'm Rob. This is my 5th year TFing CS50.
I'm Gabriel. I'm head TF CS50. I was TF last year, and this year I'm head.
And I'm Allison, and this is my 2nd year TFing CS50.
All right, so this thing on the left, hopefully you've seen it before. If not, because you've downloaded it for yourself, you should have seen it in lecture. So this is the CS50 appliance, and he did a somewhat of a description of it in lecture, but basically it's just you are running an operating system within your operating system so that we can give you programs without needing to worry, oh, is this going to work on both Windows and Mac, or if some of you are already using Linux. It's just supposed to be a common playing field so everyone has the same exact environment. So if you haven't downloaded this already, you should download it because you're going to need it for the problem set. And it is a 2 gigabyte download, so it might take a while. On the Harvard network, it'll go fast. So CS50 appliance. Now, in the beginning, we're going to talk about just a bunch of command line stuff. And so by that, I mean working in this little environment over here. And notice, so all of the things I say here, right now, are going to work if you're inside of a terminal inside of the appliance, or if you are inside of the gedit terminal window inside of the appliance. So those environments are identical. But I'm going to go a third route. And notice down here, this little IP address right here. So you don't have to do this, but this IP address, now if I, except it's blocked by this thing. Okay, God. Okay, so that IP address over in a terminal here, so this terminal over here is a terminal in my Mac. So this is in no way currently associated with the appliance at all. And if you're on Windows, then you're going to need to download something specifically for this. In particular, people tend to use PuTTY, P-U-T-T-Y. So what I'm going to do is type SSH and then that IP address. Well, jharvard at that IP address. So 192.168.224.220. This scary message, ignore it, just type yes. This CS50 in a box, it asks for your password. And so in a lot of these contexts where it asks for the password, you can, we've gotten a lot of questions where it says, it's not actually typing. It doesn't show you the characters of the password as you type, if anything for a security feature, because if someone's looking over your shoulder and they see star, 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 then they know that your password is 4 characters. So the idea is it will ask you for your password, type, it's not going to show you the characters, but it's actually accepting them. In this case, anytime you ever see a password prompt dealing with the appliance, the password's going to be Crimson. So Crimson. And now here, inside of this window that is in my Mac, I am basically having the same exact view as inside of a terminal in the appliance. So you don't have to do this. You can do everything you want inside of the appliance. I almost never actually do anything in the appliance. I almost always minimize that, and now I'm working SSH into the appliance. If anything, if you have a slower computer, you might notice a difference. I do this because I prefer this terminal window has some features like I can split the window, and now I can SSH into the appliance. Now I got 2 SSHs going on at once. So if your computer is particularly slow and you're working in the appliance and you realize, oh, this is really laggy, whatever, it tends to be much faster if you're SSH'd in. But otherwise, you can work either way. Secure shells, something like that. What does SSH mean? No, it's not.
It's just secure shell.
Secure shell. It's a protocol that it's a secure protocol, so encrypted. People can't snoop the network and see what you're saying to anything you're SSH to. And in fact, in the olden days of CS50, so in 2009 when I was a freshman, the way that you worked on CS50 problem sets was you SSH to some server that we gave you access to, and you worked on there. So you didn't have this graphical appliance, you didn't have gedit, you didn't have all of these things that you could visually point and click. You had to work in this interface. I prefer to work in this interface. So part of what we're going to be going over right now are a bunch of the commands that you should start to get familiar with as you go along in the course. And honestly, once you get used to them, it is so much faster to work in this environment than it is to work with, I don't know, Finder, dragging and clicking things. Okay, so here we are. Now, I just SSH'd in, and so the default location, we'll see, you saw some of these commands in class, but we'll go over all of them again. The default location we're in is the home directory. And directory, just another word for folder. So we're in the home directory. If I type ls, list the files in this directory. Evidently, I created a blah.c earlier. So we have a desktop directory. You notice the syntax highlighting. So this light blue highlighting indicates, make it a little bigger. The light blue highlighting indicates a directory, and the straight white indicates just a plain file. So there are going to be some other colors you see. An executable file is probably going to be green or something like that. Okay, so we are in the home directory. Now, if I want to go into a different directory, cd is the command I want. So change directory, and then you pass the name of the directory that you want to go into. So here we have 4 options. I could go into downloads. And now we see here it has updated this parenthetical to say I'm in tilde/downloads. So what is tilde? It's a shorthand for your home directory. So almost everything you do is going to be with respect to your home directory, and pwd is just a command I use once in a year that just prints the current directory. And so you see here that tilde/downloads really resolves to /home/jharvard/downloads. So /home/jharvard is my home directory. So we can cd ... Now, ... is a special directory that always refers to the one directory up. So if I'm in tilde/downloads, then cd ... is going to bring me to tilde. What do we think cd ... is going to bring me to now? It'll bring me to /home. So tilde, if I print working directory, I'm in now /home/jharvard. One directory up from that, now it says here /home. Okay? Now, cd ... Now I'm in the root directory, and you can't do it again. You'll just stay in the root directory forever. The root directory has a whole bunch of things that if you want to look into, you can. For example, if I go into bin, that contains all of these binaries, such as ls and cd and all of those things. So these commands need to exist somewhere in the system, and it's in the /bin directory. But almost everything you do is going to be from your home directory. And cd, without any arguments whatsoever, you could say cd tilde. Don't need to. Cd is going to bring you back to your home directory. I guess one last one, cd dash is going to bring you back to the last directory that you were in. So I just cd'd twice in a row, so my last directory was the home directory. If I go to /bin, and now let's go up and into user share. Let's go to user share. Okay, now I'm in user share, cd dash, back in bin. So this gets particularly useful when you have, and it'll toggle, so user share, back bin, share bin. So this gets useful. You may find yourself having many, many, many nested directories, and you want to do something real quick in an upper directory. You go to that directory, make changes and stuff like that, and now you want to go back to where you were, cd dash. I'm always frustrated when I happen to go to that directory I wanted to do work in. I always get frustrated when I did it in 2 steps instead of 1 step, because that means that cd dash is going to bring me to that intermediate location instead of where I want to go. Okay, so we see how to list files. We know how to get around so far. So now let's talk about, well, editing files. So in this course, you're almost always expected to use gedit. If you want, you can take the next step and start learning a command line text editor. So various options exist, and the ones that are probably going to be relevant to you, we have Nano, Vim, and Emacs. So Nano is the beginner's command line text editor. So Nano, let's go in blah.c I created earlier. It's just this standard C file. And you see a whole bunch of stuff going on the bottom of this screen. And apparently blah.c contains this C code. OK, so in this particular editor, what it's saying at the bottom, now this caret symbol, we see this caret G, caret X, caret O. So that, in almost all contexts that you see, you might see that caret symbol in other places online, on Stack Overflow, something like that. It almost always refers to control. So to exit, I want to do Control X. Control X, exits. And I can use my arrow keys to move around. Notice I cannot point and click readily. You need to use your arrow keys to move around. There might be a setting to point and click. But let's make some changes. Now, Control X to go exit. It's going to say save modified buffer. Now, the prompt, I can Y for yes, N for no, Control C for cancel. I'll just say yes. File name to write. The default is the file that it already is. Hit enter. OK. Now I've just edited that file, saved it, and it is changed. So Nano is the easiest text editor to get used to. The alternatives are Vim and Emacs. Those are higher level text editors that have a very steep learning curve. So my personal preference is Vim, and it has a wide variety of options. And once you get used to it, you'll never want to go to any other text editor because you just have so many things available to you in these, but it takes a really long time to learn. So maybe you just want to force yourself right now to get used to it, but I would say it's worth it, but it is hard. And then Emacs, I always struggle in Emacs because I know how to do absolutely nothing. Apparently Emacs is not by default installed on the appliance. We will probably add that as a default installation.
Update 50.
Yeah. But Emacs, once you learn one of Vim and or Emacs, there's no compelling reason to ever learn the other, but it's a completely different style. OK, so that's editing text files. Now,
All right, if we're stuck in Vim right now, how do we?
so Vim, there are multiple modes in Vim, and there are entire tutorials on learning Vim. So if you happen to be in insert mode in order to type text, which you can enter that in various ways, but I is how you get into insert mode. In order to get out of any special mode that you're in, just escape. And you just bash escape to get out of any like nested modes you're in. Just, OK, now I'm back in normal mode. And so in normal mode, a colon, you see it appear at the bottom, and then Q. So Q will quit if you've made changes, which have I made changes? I have made changes, apparently. So if you've made changes, it'll say you can put an exclamation mark. I'm going to call it a bang. So you can put a bang to just quit without doing anything, or :WQ will save and quit. So W in general is write. So write the file. I can write and quit, or you could have just Q exclam, Q bang, just to get out of there, regardless of any changes that you've made. Okay. Yep. All right. So now let's go. We can create files. Let's start removing files. And I'll just throw in one quick new command, touch. So touch foo, touch bar, touch baz. If I ls, now we see that those files exist. They're completely empty. So touch is just an easy way of, one, creating a file. Two, technically, just to state it, it updates the timestamp. So any file that you create has a timestamp associated with it. So baz was created on September 14th at 1621. It's now 1622, so if I touch baz again, we see that Baz was created, or well, Baz was most recently modified at 1622. But otherwise, I almost never look at the timestamps on files. So touch, here I'm just using it to create some quick files. All right, so now rm is the command that we care about here, and we can rm foo, let's say remove regular empty file foo, and we can type y, and now it's removed. And rm baz, remove regular empty file baz, I can type n for no, now it's not removed. So rm baz still exists, foo is gone.
Keep talking.
All right, so the annoying message here, remove regular empty, what you doing down there? Remove regular empty file. So if we don't want to be bothered by that message, we can throw in this -f flag, and so that's force. And now I can rm-f bar, and it's not going to say, do you want to remove this file? It'll just do it. And ls, I don't see bar there anymore. Now that is a potentially dangerous command. Tends not to be too bad. We'll come back in a second how it can get really dangerous. And let's create, let's make some temp directory. Makedir, another command. So makedir is a command that makes a directory. And now by ls, we see this nice light blue highlighted temp directory. And I can cd into temp, and I can makedir foo, cd into foo, makedir bar, cd into bar. So we see we can easily get into some pretty deep nesting. Now, how do I remove a directory? rmdir. So if I just straight try to rm, like we did with a regular file, rm bar, it's going to say cannot remove bar, it is a directory. There's a special command for removing directories, kind of. So rmdir bar, now bar is gone. Okay, so rmdir, I pretty much never use. So the reason being, now let's make a regular file bar in here. So rmdir foo, rmdir, failed to remove foo, directory not empty. So you cannot use remove dir on a directory that has things in it. So you have some options. You can go into that directory, remove everything manually, and then come out and rmdir the directory. That obviously sounds annoying. What if there are thousands of files in there? Well, you could rm star. We'll talk about star in a second. It basically means all the things. But better yet, so rm-r. So rm-r, in a lot of contexts, -r means recursive, which we'll talk about what recursive means in several weeks. But it basically means traverse the entirety of this directory and remove everything. So rm-r foo is going to say descend into directory foo. Yes. Remove regular empty file foo/bar. Yes. Remove directory foo. Yes. Okay. So now foo and everything within it has been removed. Now that can get particularly annoying when, let's touch 1, touch 2, touch 3. Can have a whole bunch of files. If I wanted, I could create, I don't know, thousands of files in here. And rm-r foo is going to be pretty annoying. Yes, 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 yes. With a lot more files, you quickly see how many times I have to type yes. Well, we just saw before how we can get rid of needing to type yes. -f. So makedir foo, cd foo, touch 1, 2, 3. Okay, so rm-rf foo is going to blindly remove foo entirely. No prompt, no anything, foo is gone. So I tend to use this command all the time. That said, it is a very dangerous command, because if I do something like this, it will not prompt you. It will be gone. And you know, it happens pretty frequently. And even in higher level CS courses, sometimes we'll see something where someone says, I accidentally rm-rf'd my home directory, and all of my pset is gone. And it's devastating, but there's no trash can. There's nothing for you to retrieve it. It's just gone. Even worse would be something like rm-rf/. So we just discussed that root directory. It holds all of the files on your system. Things tend to get pretty messy when you remove things like ls and cd and all of those. So
What's the difference between RM-RF and RM star?
So RM star,
Oh, question was,
Oh.
what's the difference between RF and
RM star.
RM star?
so RM star. Star in general means all of the contents of this directory. So trying to think of other ways of showing star. Well, star actually generally means match any pattern. So if I have a file called dog1, touch dog2, touch cat1, touch cat2, so ls star 1 is going to print cat1 and dog1, because that star can be filled in with the 1 needs to be there, but star can be either cat or dog. It's a wild card. That's the word I'm looking for, wild card. Where I could ls dog star, and now I'm going to see dog1, dog2. So those are listing the files that match that particular pattern. You can use ls in this way. Ls star matches anything. So it's going to print all of the contents of this directory, since all of them match. It's not going to print anything in like upper level directories. If I have a subdirectory foo and touch 1, 2, 3. So now if I rm star, remove cat1, cat2, dog1, dog2, cannot remove foo. It is a directory. So star is just a star expands to all of the files in the directory. So technically that's rm star is like saying rm cat1, cat2, dog1, dog2, foo. Whereas rm-rf, technically star would accomplish what we want, but rm-rf, if I go out of this directory, rm-rf temp, that's going to go into temp and recursively remove everything. So star is separate in that that is understood by, so this thing that I'm running in, this thing that is prompting me for commands and then executing and doing them, I call this my shell. And so this shell is itself a program, and if I wanted, I could run /bin bash. The shell is called bash. And now we notice something has slightly changed, and that's because my settings for the shell are somewhat different. But now I'm technically running a shell within my original shell, and I can exit that shell, and now I'm back to my top-level shell. The purpose of saying that is, what was the purpose of, the star. So the star is something understood by bash. So rm-rf, the -rf flag is understood by just rm. It knows that when you pass it -rf that you want it to recursively remove all files without prompting. The star is something understood by bash, that when you say rm star, bash isn't going to say, hey, rm, remove star. Bash is going to say, rm, remove cat1, cat2, dog1, dog2. It's automatically going to expand all of the files in the directory. Okay, so, and similarly, tilde is another symbol that bash understands. So when you say cd tilde, bash expands that to be your home directory. All right, other questions so far? Okay, so we're going to start going quick. Tab completion, just to throw it out there, a lot of people don't realize this exists. So if I type cd dow, I want to go into downloads. I do not need to type nloads. I can just hit tab. So it recognizes that DOW is a prefix that doesn't match anything else in this directory, so it will complete that for you. Now I can enter. And I also do that recursively, so make dir foo. Let's go into foo, make dir bar. So going back to my home directory, I can see downloads. Now hitting tab again, it's automatically going to fill in foo. It's the only directory there. Hitting tab again, automatically going to fill in bar. So now I'm in downloads foo bar. So this tab completion, whenever I go to office hours and I'm standing over someone's shoulder and they're going RM D O W N L O A D S, I'm dying. I'm just tab, 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 tab. So definitely use tab. Similarly, up and down, a lot of people they happen to never have hit up and down. It'll go through the previous commands. So if you just ran something and you want to run it again, just hold up till you get to it. Okay. So quick, some other things. Let's go back into temp. Let's create some files. So in here, I'm going to just list some words. Dog, cat, meow. Let's do dog, fish. Okay, so now grep is a very useful command that you use to search throughout files for particular text. And technically, you can do really complex expressions for it to match. So here, if I grep, and what do I want to search for? Let's say I'm searching for cat, and I want to search all of these files. So how do I do all of these files? Star. So in file 1, I have cat. I probably could have called it something better because that looks like line numbers or something. But in file 1, I have a line with cat. In file 2, I have a line with cat. So now I can look inside file 1 and see, oh yeah, that file did have cat. Notice file 3 was not matched because cat isn't in there. I can grep for meow. Only file 2 has meow. So this you can combine again with -r, which, as I said before, frequently means recursive. And so I can come up here, grep -r for any instance of, let's edit this one, just throw cat in there. So grep -r for any instance of cat throughout this directory, and it will recursively search any subdirectories. So in Baz, there's cat. In temp/2, there's cat. And in temp/1, there's cat. So that's searching within files. Now, you can also use find. And so find is specifically about looking for files with a given name. So let's make some more. Let's go into downloads, touch dog 1, touch cat 1, 2, touch cat, dog, touch cat, cat. I don't know. Okay, so I want to find all files with dog in the name. So find, and for the longest time I never remembered how find worked until I finally read something that made it so clear. So find, automatically recursive. You don't need to pass a -r. So find dot. We haven't talked about dot yet, whereas dot dot always means the previous, like one directory up. Dot always means the current directory. So I could rm-rf dot in the same way I can rm-rf star. Ultimately, they accomplish the same thing. rm-rf dot is going to remove the entire current directory. Okay, so which I don't want to do there. But find dot, so recursively search the current directory. And now everything after this are a bunch of flags that you use to exclude things from the return. So find dot returns everything that it can find from the current directory. Those are all the files recursively searching. We'll see some of those in a second. But in case you're wondering how I do that, so Command K at the very least in my terminal in the Mac clears it. Control L generally clears it for any sort of terminal. You can also type clear. And if you ever get into a weird scenario, it's happened to me a couple times, where the colors of your prompts are all messed up, or you aren't able to see anything being typed when you're typing, or because sometimes like the background color is the same as the foreground color, and now you can't see the font. Reset is something that just resets you to the default black background, white front, or whatever you set them to. Okay, so where were we? Find, dot. So now everything past this point restricts the results to something that matches the given pattern. So here I want to search everything with the name cat. Okay, got nothing. Why is that the case? Well, I'm just searching for something with exactly the name cat. If I want to search something that has some pattern and cat, the quotes technically aren't necessary, but I'm throwing them there. So now it finds cat cat, because that's the only thing that has some arbitrary pattern followed by cat. I can put cat star, and now it finds cat cat, cat dog, cat 2, because those are all the things with cat at the beginning followed by anything. You can combine this if you want to search for all C files that you have. You might do star.c. We have blah.c here. So that's how find works. You can search as a whole bunch of flags for further restrictions. And I don't know, one of them, let's say -d. So deprecated. Oh, that's not what I want, not dash D, type D. So find dash type D. Okay, so what that just did is I'm searching for all files in the current directory with a D stands for directory, with a directory type. So this returns all directories in the current directory, and type F is all regular files, all non-directories. So that's just an example of other ways you can restrict the search other than just the name of the file. It's been 30 minutes. Still going.
I'll breeze through. It'll be fine.
So some other things. Now, bang, exclamation mark. So that generally means, well, let's see an example. So bang F, what is that going to do? Well, it seems to have repeated find dot dash type F. What about bang G? That just grep dash R cat star. So bang you can use to repeat a recently done command. So it takes, if I type bang GRE, it's going to rerun the command that began with GRE most recently. And you can see all these commands if you want with history. So history, these are all the commands I've run today. And, well, it's not literally restricted today, but I've only used this appliance as of today. It's your entirety of the history of your bash shell, except it cuts off at some point.
What happens if you do history and it puts up the commands and there was an error as a result of it? Will it still print the...
Yeah, so if there was an error in one of these, commands,
He's got.
it doesn't, so let's say, I'm trying to think. That is an error. Command not found. Still appears in the history. Yep. All right. Other questions on anything? Okay, so that's bang. Now, really useful command, man. So that gives you the manual for a given command. So let's say man ls. So this is showing me ls. It lists directory contents. And this is where I see that there are these various flags that exist. So we see that ls-l exists if we were to read that. ls-l gives me this full listing of the directory with who owns the file, the size of the file, the modified timestamp. So ls-a is another one that you might actually use somewhat frequently. -al is my most common flag as past ls. So -a, notice this is a lot more files than just ls, ls-a. What's in common with all of these files? They start with a dot. So this is a convention in Linux that files that begin with a dot are hidden. So it just means that when we just straight ls, or if we're searching this directory using the Finder equivalent or the Windows Explorer equivalent, that we don't want to see these dot files. They just pollute the view of things. So they are hidden unless you specifically request them with something like -a. So I can cd into .local, and I see that that is itself a directory with a shared directory and applications and blah, blah, blah. So dot files, they're just hidden. Okay, so other important ones. I have a couple I can skip. Let's just real quick talk about the file redirection things. So there's a whole complex series of things you can do with these. But just to see them, let's say echo, another command, really dumb command. All it does is print what I tell it to. So echo hello. It just echoed hello to the screen. Hello world. Echoes hello world. So one command, or one symbol that bash understands is this greater than symbol, and that is the output to a file symbol. So if I output this to foo, there's now a file called foo, inside of which is hello world. So notice that when I echo hello world pipe into foo, it didn't echo hello world. Instead, it was put into the file foo. And another command, just to throw it at you, cat, that's an easy way to just completely list the contents of the file so that I don't have to open a text editor to view it. So the contents of the foo file are hello world. And I could cat blah.c, the contents are this. So again, just these are commands that don't expect you to have them all memorized. The idea is you've seen them. Maybe you're working on something, you're like, I'm sick of opening this file. I wish I could just look at the contents real quick. You could do that, then look back and say, oh yeah, I remember something like that exists, and it's cat. So that is going to a file. Now there isn't really any good example. of reading from a file yet. What's something that takes something from standard in? Any simple Linux command. I don't know. When we get to it, in a couple of weeks, you'll have a piece, or well, this week, you have a piece set where you start taking input from the user. And so usually you type that input at the keyboard. Instead of typing that input at the keyboard, you can instead pipe in from a file so that when you do Mario, /Mario, pipe in from any given file. And that's going to run the Mario program, not expecting input at the keyboard. Instead, it's just going to read the lines from the foo file. So greater than foo puts it into the foo file, and less than foo takes stuff from the foo file and uses that as input to this program. And just to see it, we could also echo foo bar baz, and then instead of 1 greater than, let's do 2 into foo. What does that do? It just appends to the file. So instead of, notice if I do echo blah into foo and then cat foo, it's just blah. So when you output to a file, it completely overwrites that file. If you just want to append, double greater. And last is pipe. Pipe gets much more complicated, where it takes the output of one command and feeds it into the next command. So some common thing, history. So I don't want to look at this. What is a command that, or show me all commands in my history where I grepped for something. No, that's confusing. Show me all commands where I, find. All find commands I ever ran. So find, or history. Now history outputs to the screen this list of commands, but I don't want to output it to the screen. Instead, I'm going to pipe it into grep. So let's grep for all instances of find. Okay, so this now, instead of grep taking the input, grep is able to handle as input, I don't know. We're using grep slightly differently here. So instead of typing the list of things we wanted to search for, instead grep is taking as input. So if I do just grep find, it waits for me to type things. So cat, hello, find, hello, find. Notice every time I type find, it recognizes that I typed find. So instead of this, we'll search files for find. So history is now going to output a list of all commands. And then we're putting that output, and we're feeding it to grep. And so it's spitting out all instances of find. Notice the reason I said it'd be confusing is if it's still confusing. If I grep for grep, and it's also, notice it's pretty much always showing the command I just ran, because that command itself has grep inside of it. Okay, so any questions on anything, and I'll transfer it over at this point. Hopefully this is a nice overview of all commands that you don't need to have memorized, but these make up a solid 95% of what I do at the command line. Also keep in mind that the command line itself, Bash is a programming language, and so when you get down to it, you might want to do really complex things, and so it has things like loops and ifs and all of those that you're going to get used to with your programming languages. But that is beyond the scope of this section. Okay, so no questions?
None? I can do it on mine if you want. We can see what happens.
Off to Allison.
Woo! You're a hard act to follow, Rob. Do you want me to switch with you? Or you got it? Okay. I'm going to try not quite be as lengthy there. Okay. Let's see if this will work the way I want it to. Maybe. Haha. Yes. Okay. So I'm just going to very quickly go through variables, loops, conditionals, and a little bit on the compiler. If you have questions at any time, please stop me. These guys will remind me to repeat your questions in case I forget. But shouldn't be too bad. So variables, yeah. We have, one of your Scratch pieces here. I'm sure most of you, if you had some sort of game that you created with Scratch, you had to keep track of something like score or time or something like that. So those bright orange pieces that we see there are just the Scratch form of variables. And you will definitely be using variables throughout your programs. If you're not, I'm not really sure what you're doing. So, but anyways, so big thing defining variables. With C, every variable has to have a type declared. So I gave you a very general one at the top. So you'll have your type and then whatever you decide to call your variable. So in this case, a type in your variable list. We have 3 examples, char of some grade of an A, which is what I'm sure you all want to get in this class. So you can define multiple variables on one line as long as they're all of the same type, which is our second example there, where you have 3 variables, x, y, and z. They're all floats. And then you can also, in this last example with int score and number of teams, you can initialize them right there. So in the middle example where we just have float of x, y, and z, those are not initialized yet. They have no value, or they have garbage values. And if you try and use them, your compiler will yell at you. You have to both declare and initialize your variables. So in this last one, we're doing both. We are declaring variables of score and number of teams, and we are initializing them, giving them their initial values of 7 and 4, respectively. Cool. Everyone good? Awesome. Okay, so some conventions. If you guys have read through Style 50, these are just things that we'd like for you to implement in your style. So meaningful names. If you start calling things just X, Y, and Z, especially as you get into lengthier programs, you're probably going to confuse yourself and be like, what is this variable referring to? Like, I have no idea what this means. So if it's meant to hold a score, call it score. If it's meant to hold some answer or result, give it a name like that. For loops, which we will get into in the next slide, single letter variables are fine.
It's I, J, and K are just
I, J, and K are
conventions for for loops that everyone expects them to be called I, J, and K. You can call them, I see row column, or like row call sometimes for 2 nested loops, and that's also kind of standard, but I and J is completely understood.
Yeah, I and J, you're totally fine. For sake of clarity, like in some of your P sets, it might make sense to have more descriptive things in there just to keep track of it. But I, J, and K, I think the vast majority of us all use.
Yeah. With these conventions, so style is important. It's one of the 4 axes on which you're graded, and it is so easy to just go over your P set at the end and make sure that there aren't stylistic mistakes. So just make sure you're tabbing correctly. Make sure your variables are named fine. Leave some comments. It is very easy to get those points. You don't have to think about anything in order to get those points. You don't have to figure anything out. It's just making it look pretty.
In fact, we have Style 50, which will tell you where you're messing up if you're messing up on style, and will tell you exactly what you need to fix and how you need to fix it. It's also just good to mention that it's course policy that if you're at office hours and your code is a mess, we can decline to help you till it looks nicer. So start out right, keep consistent style. You're also just going to make your lives a whole lot easier when you're trying to go through and debug. If you're trying to figure out where you're missing a curly brace and they are all over the place, you're just making your own life harder. So be consistent with style. I promise it will make your life easier. It'll make our lives easier. Everyone will be much happier, and that's what you want.
Your grade will be higher.
Yes, and your grade, if your TFs like you, tends to be, favorable. All right, and then just the second point here, consistent initialization. So as we saw, you can declare and initialize things, multiple variables in the same line. One thing we would like you not to do is to declare some variables and not initialize them on the same line that you are initializing others. So in case that made no sense whatsoever, we have the example here where we're declaring int variables of quarters, dimes, and pennies, but quarters and pennies have no initial value. We haven't initialized them, but right in the middle there, we already initialized dimes to 0. So either do quarters, dimes, pennies, or do quarters equals 0, dimes equals 0, pennies equals 0, or whatever those initial values are. Big thing with style, like be consistent. Like when in doubt, be consistent. But follow our style guide too. Cool. Everyone good there? The style guide is what's
I think
the
it's
website?
manual.cs50.net
Slash style.
style. Yep.
Yes. So question, where is style 50? Manual.cs50.net/style. Yes.
And if we're defining variables, is it okay if we put like redundant code, like int score, and then int goal? So would you say that no, you gotta like define them together?
So question, should you have redundant code when you are defining variables such as int score and on the next line in game?
There are definitely cases where redundant code is bad. I would not consider that redundant code. I almost never declare multiple variables on the same line, ever. And if anything, it's because usually I leave some sort of comment explaining what the variable is for. So I'll say like int score, // keeps track of whatever. In total, //. So it's much grosser in that way to put them all on the same line. I just never put them on the same line.
I feel like it's personal preference at the point.
Yeah.
Like,
Does that go for like for loops and stuff too?
So like inside, like int I equals 0, comma, length equals something, that you don't have a choice. With for loops, the initialization part, so you might have only seen int I equals 0, semicolon, I less than whatever, semicolon, I plus plus. That int I equals 0, technically you can also do what we saw before with the comma syntax, int I equals 0, comma, j equals 3, comma, k equals 5. You don't have a choice to split that up into multiple lines, and that's standard. Seeing it there is fine.
awesome. Well, convenient segue into loops. So yeah, here we have, just some examples of loops that you guys saw in Scratch. And of course, all of these can just be recreated in C. And they basically allow you to repeat some section of code until a certain condition is met, which we will get into right after talking about loops with conditionals. So we have three main types: for, while, and do while, which we will all go through right now. So first one is for loops. So for some condition, execute this, block of code. And we have this cool little diagram here at the bottom. But basically, you have in your for, that first line, you're going to initialize your variables. So as we talked about, like I is equal to 0 or I is equal to 10, whatever you need that variable to be, it's going to be initialized there, declared and initialized to some value. So and then we have some condition that's going to be checking our variable against something. So in the typical case where maybe you want this section of code to execute 5 times. So we'd have int I equals 0, and we want it to be when I is less than 5. So that condition is just going to check that every time. If that condition evaluates to true, it's going to run the code, which is exactly what this little diagram is showing. And so it executes it, it updates the variable, which is what we see in the last part of our for loop initialization there. So it'll just keep doing this until that condition is not met, and then it will exit the loop and continue moving on with the rest of your program. Everyone good there? Cool. So here's an example, very similar to something I just talked about. So we just want to print, this is CS50 10 times. So as you see here, we have our for, and then we initialized a variable I to be equal to 0. Our condition is checking that it's less than 10. So it'll evaluate to true when we first start, and then updates our variable each time that it actually executes and prints out, this is CS50, and will terminate after 10 times. Cool. So while loops are up next. And as you see here, we just have some while this condition, oh, question?
How can I jump actually just not one number, but 2 numbers, for example? I plus plus?
So the question was, how can you update your variable by more than one at a time? So I++ will update by 1 each time. If you wanted to update it by like 2, you could do I plus equals 2.
Have you seen plus
plus
equals
equals?
in lecture yet?
Okay, so you could do, it's effectively the same thing as I equals I plus 2. So it's going to take it and update it by 2 each time. Plus equals is just something we call syntactic sugar.
Yeah, those exist for pretty much all arithmetic operators. So I times equal 2 would double the number. J divide equals 3 would divide j, but is the same as j equals j divided by 3.
Or minus equals 2 would decrement I by 2 each time.
Even mod equals, or
Yeah.
you haven't seen bitwise operators, but like caret equals and ampersand equals, all of those exist.
Right. So that a lot of the times, especially with your first couple of p-sets, you'll be probably incrementing by 1. So I++, j++ are all things you're going to typically be using. But that update condition is fully within your control. You can update it by whatever increments or in whatever way you decide to. Maybe you even want it to be a random number sometimes. Who knows? But yes, there are lots of things you can do with that. You're not
And-
restricted to I++.
Just so that you know it exists, it also exists in another form, ++i. So if you ever searching online and happen to see ++i, but pretty much means the same thing.
Cool. Good? Awesome. So while loops, very similar. You have some condition. The main thing to notice here is instead of having like 3 different parts to set up, we have 1. We just have some condition that's being checked. And in the same way, as long as that condition evaluates to true, your code is going to run. And if it's false, it will terminate, move on to the next part of your program. So this is kind of like, what's a good example of checking for just some normal condition?
All true.
While true. You could do while true. Well, while 1 is equal to 1. Anyways.
You do while, just instead of using a for loop, you can always code a for loop in a while loop. So while I greater than 0 or while I less than 10.
Yeah. Awesome. And then we have do while loops, which is great for user validation, where you kind of want to get something from your user, see if it's valid, and then continue from there. So one of the things to know is with a do while loop is that it's going to execute, and then it will re-execute if this condition is met. So probably the best way to do this is just to see an example here. So as I just mentioned, user validation is really useful, or do whiles are really useful with user validation. So this is just going to reprompt some user until they enter a positive number, which might be useful for your p-set this week. And so, in this case, when we initially run this program, it's going to print enter a positive number, it's going to get some input from the user, and then it's going to check that input against the condition that you've set for it. So in this case, it's going to say, okay, is our input negative, or is it 0 or negative, which would be invalid, so then it would reprompt. Question?
Is this the same then as a while loop if you just copy that code and put it above the while loop?
Wow. So question was, would this be the same as just a while loop if we were to just copy the while loop above? So in this case, your while loop is going to check the condition first. So it's going to say, in this case, if we tried to write this just as a while loop, it would say while input is less than 1, but we don't have an input yet. Or,
It's like if you, a while loop, including this code, but then you copy the code and paste it above the while loop also. Like above the, so
Yes.
if you just
Yeah.
add this
Yes.
code,
That's the
Yeah.
same thing.
then while loop.
Yeah.
it would be the same thing, yes. So you could just write, instead of having a do, yes.
Yes.
You never.
But that's more elegant.
Yeah, that's more elegant. You can get into design and whatnot, but yes, you can totally do that. Any other questions? Okay, cool. So we've talked a lot about conditions with all these loops that we have. So we're actually getting into conditions and Boolean expressions. Again, you use these in C, so just kind of transitioning from the more graphic interface to actually coding. Cool, so big one, if. Basically just allows us to introduce some logic into our program and checks this condition. So in this case, okay, is n greater than 0? Yes, it is, so you can execute this. It's just checking some condition that you've set, which I think everyone's comfortable with checking conditions. Cool. And then, awesome. So if else is your other one, you can say, okay, if this is true, do this first thing. Otherwise, I want you to default and do something else. If you, in this case, you either pick a positive number or a negative number. You only have 2 options. you need it to execute like regardless of what your user inputs. So you can say, well, is it greater than 0? Cool, print a positive number. If it's not, print a negative. Everyone good? And then one thing to recognize is that if the if condition is met, the else will never also execute. Only one of these will execute at a time. So it's a trade-off. You don't get to have both. You either have the first condition, you either have the if or the else, not both. Which then can make things even more complicated because you can do if, and then else. So in this case, we have 3 conditions. And again, only one of these is going to end up being executed. So you might be wondering, like, well, what if you have something that can meet like 2 of these? Maybe whatever you're inputting meets both the condition for if and the else if. The only thing that's going to run as soon as it finds something that it meets the condition for, that evaluates to true, that's what it's going to run and nothing else. So if you had like, is this number between 0 and 5 for your first one, or is this number between 3 and 5 for your second for the else if part, and you input the number, I said 0 and 5 and 3, 4, it's going to hit the first one, it's going to say, okay, this number is between 0 and 5, execute and leave. It will never hit that second option. Cool? Awesome. Okay, we also have switch statements if you want to get even more, switch is next. I'm getting ahead of myself here. Again, multiple if blocks, whereas I just said is as soon as you find a condition that's met in an if, else, it leaves. If you need to check multiple things, you're going to want to use ifs because it will check every time here. So this will run through, and if it's greater than or equal to 90, it's going to print that. And it will run through and check every single one of these.
Yeah, so this would be more buggy than you want, or would this be what you wanted?
This, I mean,
What was the
the
question?
question is, would this be buggy or does this do what you want? It really depends on your what you want from your program.
I mean, like, if you put 90 in.
If you put 90,
You're gonna get 2 things.
you're going to get 2 things.
Two.
Yes, 2.
2?
No,
You're
So
going to
you're
get
gonna
4.
4.
If you put 90, it's going to
Yeah.
say you got an A, you got a
A
B, you got a C,
C,
you got a
a
D.
D. Right. So it depends on what you want from your program. Sometimes you need to, check multiple things. You'll get much deeper into like what good design is as you go forward. The important thing to realize is that like this will check all 4 conditions here. Whereas if this were an if, else, it would hit that first case, it would print you got an A and be done.
Even if we decided to change this to if n greater than or equal to 90, if n greater than or equal to 80 and n less than or equal to 89, if n greater than or equal to 70 and n less than or equal to 79. So that will be correct. That will do what we want, but it still checks every single if. So whereas in the first scenario, if we enter 90 with just if, else, if we enter 90, then it's going to correct, it'll check the first one, print you got an A, skip everything else, because it already found one that works. All cases are mutually exclusive based on if, else, if. So it'll execute the first if, then it's done. It'll go to the end. Whereas if we change this to be what I was saying with like less than or equal to 89, it's going to check the first one. It'll print. I'll check the second one. It's not going to print. Check the third one. Not going to print. Check the fourth one. Not going to print. So in that case, the else if version, since these cases are mutually exclusive, it's better to use if, else if, because that is going to have fewer checks of the conditions than this version.
Yep. Cool. Awesome. So another thing we can do is switch statements. That basically a switch statement takes in some variable, in this case it's n, and determines which case to execute. So this is also one where your cases should be kind of mutually exclusive. So in this case, if we have some int, if we get a 1, it's going to match whatever that variable, whatever the value of n is to one of these cases, so 1, 2, or 3, and print out the corresponding line. And then if you notice here, we also have a default, which you can kind of think of as like your else, So if you pick any other number besides 1, 2, and 3 in this case, it's just going to print invalid. So you'll get into deciding when to use like ifs versus if-elses versus switches is going to be something that like you guys will see design-wise as you start writing more complicated programs. And there's no hard and fast rule of when to use them. It really depends on your context.
And just to throw it out there, since it is a more comfortable section, so switches, they tend to be, so you're limited in the number of ways you can use them, because ifs, the condition can be pretty much anything you want. With switches, the cases have to be numbers, or technically they can be chars too, but chars, as we'll see, are just numbers. So they have to be numbers, but switches are really more efficient than if, else, because even taking the example before of, well, the great example isn't good. Well, let's say here, we instead do this as an if, else if scenario. So if n equals 1, print you picked a low number. Else if n equals 2, you picked a medium number. Else if equals 3, high, else invalid. So let's say that was our scenario. So let's say we enter 4, so we expect invalid. The way that the if, else if approach is going to work is checks the first condition. It's not satisfied, so we check the second condition. It's not satisfied. Check the third condition, not satisfied, so we go to the else and print invalid. The way the switch works is it compiles down into what we're going to call a jump table. The main idea being that when you enter 4, it can immediately go to the default. It doesn't need to check, am I case 1? Oh, nope, that's not it. Case 2? Nope. Case 3? Nope. Default. Oh, okay, this must be where I want. And then execute that. No, it immediately jumps to the default. Or if I enter 2, it's immediately going to go to the 2 without needing to go through case 1. So in that way, realistically nowadays, that's not that much of an efficiency gain. Usually computers are pretty fast, and that's not that great. But it is the case that switches are faster. If you're really trying to optimize, use a switch.
Yep. Cool. And then we have ternary operator. So I know I mentioned earlier the word syntactic sugar. So it's just things that make your code, much more concise. So this is one of those cases. So ternary operator is question mark colon, as we see in the line string s equals n greater than 100 question mark high colon low. So basically how this works is it's the n greater than 100 is a condition. So I think it kind of makes sense. It's like asking a question. It's saying, oh, is n greater than 100? Who knows? And if it evaluates to true, it's going to give you the first thing that's listed there, which is high. Otherwise, it's going to give you low. So this is just a really simple and efficient way to kind of do like an if-else. That's exactly, this is all this is. And if we were to write this as an if-else loop, it would just, or if-else conditional, it would be if n is greater than 100, return high, else return low. This is just a much more concise way of writing it.
So this particular example, is whenever you are doing something like this, this is the pattern where I use ternary very frequently. And I hate seeing, so we haven't talked about scope yet, but I hate seeing string s semicolon. If n greater than 100, s equals high, else s equals low. So that pattern, those 5 lines of code, literally 100% of the time it can be transferred into what was up there with a ternary. So the ternary, 1 line of code. The if-else, 5. So that's an example I point out every single time. Like, this would be a great place for a ternary operator. It's so clean, but people tend to never use it.
Use it. Great.
Okay.
Take it away, Gabe.
Cool. So now you guys all learned in lecture this week that everything in a computer is binary, right? Just like the lamps here. You can be either turned on and off. And by everything, I mean literally everything. So numbers and chars and strings and even the code that you write, like inside of, like when it gets compiled to machine code and stuff like that. So it all boils down to zeros and ones. And so when we're dealing with integers, which is something that's technically very simple, we should be able to do stuff like adding them, which is probably one of the simplest things you can do to 2 integers, right? So addition and subtraction works just like it works in decimal notation, except here is with is in binary, right? So it's in base 2. So you like add 1 plus 1, that gives 0, and 1 carries over, and just keep doing that. So now comes the more interesting question. We know how to represent all positive integers in the computer, but let's make this an exercise. Pretend you guys are all in 1960 or something trying to create a computer, and you have to come up with a way of storing -1, for example, or minus any integer for that matter. How would you do that? Any ideas? Like, just throw anything at me. Yes? You can designate a special bit, which will be 0 or 1. Let's say 1 if it's positive and 0 if it's negative. And then the rest of the bits is just to store the number. Cool. So that's a very good idea. We have, I don't know, 200. And if the first bit is turned on, then it's plus 200. If it's turned off, it is minus 200. Cool. There is only one small problem with this, which is if we try to sum things up. So imagine we have, I don't know, 1, 1, 1, 1, 1 here. And we're summing this with 0, 0, 1, 0, 0, whatever. If those two are positive, that's fine. But then if one of them is negative, like let's say that this bit here is the one that's responsible for, I'm going to make it separate. So this one means that this number here is positive. This one means that this number here is negative, right? But then when you're going to sum them, you need like an if statement saying, oh, if this is 0, then my sum will be something different, right? So there's a slightly more clever way to do that, which is called 2's complement. So basically what we do is we define -1 to be the thing that if we add up to 1 gives us 0. Let me repeat that. So let's say that this here is 1. What is the thing that naturally, in like positive integers, added to that gives us 0? What if we try to add it to this number? We're going to have, okay, so let's add. We're going to have 1 plus 1 is 0. And then it carries over. And then we're going to get 0 again. I'm getting confused. And you're going to get 0 and 0 and 0 and 0 and 0 and 0. And lots of zeros. And at the very last one, we're not going to be able to carry it over because, let's say, we're only dealing with 1 byte, so only 8 bits. So what the computer does by default, it just forgets about that carry. Okay? So this is what is called the 2's complement. We simply define -1 to be the thing here that is that added. If you add that to 1, would give you 0. And so that's pretty cool because we don't really need to implement a different type of sum depending on whether that's a negative or a positive number. Does that make sense? So one thing that we do here in order to convert between a positive and a negative integer is then we flip everything and then we add 1 to that number. If you try to do it yourself on a piece of paper, you're going to see that makes sense. But if I take this number that's, I don't know, here this is 4, 5. So if I flip everything here, so 1, 1, 1, 1, 1, flip, 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 and then I add 1 to it, I'm going to have exactly -5. Okay, this kind of makes sense because if you try to sum this with the number that we had before, which was, let's flip this again. It was 1, 0, 1, and lots of zeros. If you try to add these two numbers together, you're going to have exactly 0. Okay, any questions? Cool.
The other way you flip and subtract 1?
What do you mean?
From negative to positive? You flip and add 1?
No, you flip and you add 1 always. Yeah. Okay, so characters are also encoded in binary. We have ASCII table, as you also saw in lecture, right? So it's basically a mapping of things. And here I can't emphasize enough that for a computer, A and 65 are literally the same thing. Okay, so if I write something like char c equals a, like I could at the same time just write 65 here, and it would be exactly the same. Okay, there's no difference whatsoever. We usually tend to put characters in variables of type char, not because they're like essentially made for that, but because of human convention. Okay, but you can just deal with integers instead of variables of type char, and you'll be fine. The only difference, actual difference between a char c and a int I is that an int has 4 bytes in most systems, while a char has 1 byte. Okay, they're essentially the same thing in terms of data. So what we'll print here we're printing a digit using printf with a plus 1, and just like integers, chars can be summed, so characters can also be summed. So this is exactly 65. So this is going to be 66, and here we have 65 plus little a minus big A, which will be, I don't really know, but it will be exactly the gap between the like capital letters and the smaller letters. So we're going to get small a, right? Yeah. So this is going to print a character, which is exactly this one. Good? Any questions? So here, we have a bunch of different types for numerical variables. We already talked about int. Float is just a way to, so we have, this is really funny, because when I first learned to program back in the day with Python, like the first program that I ever tried to write, I saw that there was a type called int and a type called float. And the float was for all real numbers. So then I asked, why should I ever use an int then? Because if I can use all real numbers with a float, I would just stop using ints, right? Because real numbers are much like more generic. It turns out that this is not the case in computers, because you can't really, they're essentially different things. So integers and floats, the operations that you do to them are essentially different because of the way that they are stored. Okay, we're going to talk a little bit more about that in a second. So double is just a bigger float. Usually most systems, a float is 4 bytes, just like an int, and a double is 8 bytes. A long is actually just a symbol that you append to a type like int. You say long int, like this, long int x, to make it longer. So in most systems, that will give 8 bytes instead of the usual 4. And you can actually drop the int, so you can just say long, and that works too. Okay. You can also do other things like unsigned int, or again, just unsigned would also work, and that will make x be a variable like everything is positive, so you can't really have negative numbers in the way that we saw up here. So floating point precision. That's one of the reasons why you want to use ints instead of floats, because ints are 100% precise, right? It's exactly that number. For floating points, if you say answer equals 1 over 10, I happen to have this exact program here, float.c, that prints to 20 decimal places 1 divided by 10. And that usually is 0.1, right? But here, if we make float, and then we run it, we see that it's not exactly 0.1, it's 0.10149 something. And why is that? Okay, because you can't really represent every single possible real number in memory because there are uncountably many of them. So we basically, we're technically only able to represent a finite amount of them with a finite amount of data. But it's really interesting. Now, this begs the question of how you would go about representing this with bits, right? So how are floats stored? With integers, that was easy. But with floats, you want to maximize the range, and you want to be able to represent, I don't know, huge numbers and very tiny numbers like 0.000001 at the same time. So again, same game. Does anyone have any idea how we could go about representing float in memory? Just throw anything. Yes, please.
Having like one, as if it was 2 ints and one being like the units and one being everything after the decimal point.
Okay, cool. So two different integers. You can have like 12.45. So that's 12 and 45. Nice. What would you say? The same thing? Yeah.
Store it essentially
Scientific notation. Yeah, that's usually what happens. So this is what is called the mantissa. That's like what comes, what is actually the number. And then the exponent is just where the comma is, right? So this is going to be something of the form, I don't know, 1, 2, 3, 4, 5 times 10 to the minus 4. I just realized that, yeah, exactly. And then this 10 to the minus 4 is going to define where the comma is, okay? In Brazil, we use comma. Here, you guys use dot, so dot. And this is cool because then you can focus lots of your bits on this guy here, on the mantissa, and then that's going to be your actual precision. And you can do this either in decimal or in the binary-based system. Like, there are different ways to implement this. Questions? Yes?
How many places after the decimal point is float precise? How many places after this?
That's a complicated question because it's never really 100% precise. Because as you see here, for some numbers it is 100% precise. I believe if we put 0.5 here, it's going to be 100% precise. It's going to be 0.5000000. So in that case, it's perfect. But in other cases, it's much less perfect. In my experience, like up to, I don't know, 4, 5, like decimal places, it's pretty precise. If you use a double, it's going to be way more precise than that. Okay?
So just to throw some more context at floats, I never remember 100% how the spec of floats actually works, but I do always remember that floats start getting messy. The range, so the idea is that when you get really, really big numbers or really, really small numbers, we start getting worse and worse at differentiating between two closed floats. So that's how I like to think about it, is like with floating point and precision, there are two floats that if I try to specify them in C, despite the fact that they're different numbers, they're going to be interpreted as the same number because we can't store them differently. We need to use the same bits. And so when we get to really, really large numbers, talking like 10 to the 300 or something, that it's at that point that like 10 to the 300 or like 5 times 10 to the 300 can't be differentiated from 7 times 10 to the 300. So that's a pretty big difference between the two numbers. But then when you get down to the normal range, things you tend to be pretty good at differentiating. And then when you get down really small, you're also getting pretty bad again. So like a whole bunch of 0.00000, it gets pretty bad.
Yeah, so a quick note, never do this. Never try to compare floats using equals because even if they're almost the same is not the same. So what you usually do is you subtract them, take the absolute value of that, and see if that's smaller than 0.0001 or something like that, okay? And cool, I know a lot of people have some background in Java, especially the ones who did AP Computer Science, right? And Java is a language that's mostly based on C, but it has a couple of very big differences. But like for loops and ifs and stuff like that, they're all the same syntax. I have a few programs here to show this. So for example, a simple hello world. This is the hello world in C, which you guys are definitely familiar with, and this one is in Java. So in Java, we have this public class hello world and public static void main and string args. The string args are going to appear in C very shortly, but let's not go there yet. Right now we have void here, which means that main's not taking any arguments. And then we have system.out.println, and that's kind of the equivalent for printf. Here we don't really need the \n because println does that for you. It puts it appends the \n at the end of the line. But if you go into something like a for, you're going to see that they're pretty much the same thing. So initialization and the condition and the update. I missed a space here. They're pretty much the same thing, except Java has a few like more high-level stuff, right? Here we can do plus I, and Java will automatically make this I here, which is an integer, into a string, and then append the two strings together. Here in C, we need to do the %d, and just notice. Lost. I need this. Yep. But the line here, the for looks exactly the same. And if we look at if, the ifs also look exactly the same. Right? So the real big differences are in those things that you see here, public static void and then public class if. So Java has what is called a virtual machine, and it is very heavily based on what is called object-oriented programming, which is a very, very common paradigm for programming nowadays. And this class thing is what you see something from object orientation, is you create a class and then you can derive objects from that class. We're not going to talk too much about that in CS50, but that's definitely something really cool, especially if you want to go into like more sophisticated web development at the end of the course, like to make your final project and like some nice frameworks and stuff. So basically the idea is that you don't want to re-implement something, so you create something that's very generic, and then you, like a shape, and then you create different shapes from it. And then from each of these shapes, you create some more specific, like shapes in 3 dimensions or something like that. So, and they have this hierarchy. They inherit from the other one. So all functions and all variables that the big shape here has, all of these are going to have, and all of these are going to have, and so on and so forth. So that's the basic idea. C doesn't have that, but C++ does have that kind of feature. And Java is heavily like influenced by object orientation. So that's why you see class here all the time. And the other thing is this Java virtual machine. So this, I think, is a very smart idea. So what the folks who invented Java did is they didn't want to compile their code twice if they had to run it in a Windows or a Mac or a Linux. So what they do is they literally run something like the appliance, but like you don't really see it happening. So they run a virtual machine inside of your computer, which is basically like a mini operating system. And that operating system's purpose in life is just to run what is called bytecode. So instead of in C, the way we would compile this is make if, and then run /if, /if. I forgot the \n. In Java, you would do first Java C to compile it, if.c. It's not C, it's .java. And then you have to run not / you get this new file if.class, but you can't really run if.class now, just like we did before. This is not an executable. You have to feed it into a program called Java, and that program is the virtual machine, and then you do if.class, or just if it, yes. And then it works. Okay, so this is kind of the virtual machine happening. C does not have that, so if I were to put this program in a Windows machine, it would not work in C. In Java, it does. Questions? Cool. That's it for our super section for today.